So now let's talk about multiple events. So eventually we're going to be talking about not if you just pull one, thing randomly, right? You're not selecting one thing now. You're going to be selecting more than one. So that's the kind of the idea that we're going with now. So these are the two or three-ish ideas that we have if you are selecting more than one individual or subject, whatever you're talking about. All right. So first, we got to talk about independent. So independent means we say that two events are called independent, provided that the occurrence of one does not affect the probability of the occurrence of the other. So independent means that one does not affect the probability of the other. And if they're not independent, then they would have to be dependent. And these go along right with what we would think, right? So a vernacular for independent, another definition for independent could be, right? So if you think about in the government, if you're an independent, then you do not affect other people, right? So you are a person on your own who does not necessarily affect other people. However, dependents, right? So dependents, especially when it comes to the government, these are just our children. So children are affected by their parents, right? If a parent goes somewhere, especially if it's a little child, the dependent has to go with them as well. So they are affected by what the parent decides. So if that didn't make any sense, don't worry about it. But sometimes that helps some students. All right, so independent means that one does not affect the probability of the other. Dependent means that it does. So notice that just because two events affect one another, it does not mean that one causes the other, right? So just because the probability is affected, it doesn't mean that one event will cause another event to occur. And we'll see some examples later on. All right, so let's look at some examples. Determine if the events are independent. Two families giving birth to baby girls. Well, one family giving birth to a baby girl would in no way affect another family giving birth to a baby girl, right? So these would be independent. Picking a card from a standard deck and then picking another card without replacement. So the word here that we're looking at is without replacement. What does without replacement means? It means you don't replace it, right? So you take out a card and you do not replace it, right? So because we have one less card, the probability is going to be affected, right? So this will be dependent. Because in general, right, if you have a standard deck, that's going to be 52 cards. So 52 cards will be the population or the bottom number, right? That total for the first card. But when you pick out a second card, if it's without replacement, there's only going to be 51 cards, which will definitely affect the probability. Part C, picking a card from a standard deck and then picking another card with replacement. So we see the only difference here is with replacement. What does with replacement mean? It means that when you take out a card, you make sure to put it back. So we take out a card from the first time, we have 52 cards. If we put it back, we still have 52 cards, right? So nothing would affect it. The probability stays the same. So this would be independent. The probability is not affected. All right. So Josh randomly picks a number 0 through 9, and Bridget randomly picks a number 0 through 9. So arguably, Josh and Bridget shouldn't be affecting each other when it comes to picking numbers. They should just randomly be picking two separate numbers, have nothing to do with each other. Now, you may be thinking, well, what if Josh has a crush on Bridget? And then Bridget says, oh, I got a 5. And then Josh says, oh, what? Me too. Crazy. That's thinking a little too much into it, right? Remember, statistics, you can always figure out a way to confuse yourself. So in general, if they're randomly picking a number, they shouldn't be affecting each other. All right, getting a heads on a coin flip and getting a 4 on a die cast. So a coin should in no way affect a die, right? So once again, these are independent. Randomly picking and eating a yellow M&M from a bag, and then randomly picking and eating a green M&M from the same bag. So would this be independent or dependent? So it didn't say with or without replacement, but it did tell us which one it is. And it comes from the word eating and picking, right? If you pick it and eat it, is that going to be with or without replacement? So if you're eating it, that's going to be without replacement, right? Unless you're just thinking that you're going to regurgitate it back into the bag, which would be really gross. So since this is without replacement, right, we're going to have one less M&M from the total, so the probability will be affected. So this will be dependent, excuse me. All right, so let's start talking about multiple events. So what is the probability of finding multiple trials? So this is just a straight off, how many, you have more than one events that you're trying to get. So in general, what we will do is we're going to multiply the probability of each trial, considering whether they are independent or not. Because remember, if they're independent, the probabilities won't change, so we're fine. But if they're dependent, they will change. So we need to keep that in mind. So here's the strategy for the multiple trials. So here's two different ways of kind of thinking about it. So one thing you can ask yourself is, where's the and? Another way that we can think about this is to tell yourself a story of the events occurring. So it's either asking yourself, where's the and, or telling yourself the story of the events. Now, the reason why we're doing this is because ultimately what we want to do is change our perspective from a group of subjects to a list of individuals. So I promise this typically is not hard. The only problem is that when students see these when they see these problems, they think of them as a group instead of individuals. So ultimately, these questions are trying to get you to go from thinking of them as one group of 15 people to 15 individual people. Like I said, it'll make more sense when we go into the problem, but this is the strategy when it comes to it. As long as you can get this down, going from a group to individuals, the rest should be okay. All right, so suppose you flip a fair coin twice. What is the probability that you obtain heads on both flips? That is, a head on the first flip and a head on the second flip. So if I just ended it with this question, right? What is the probability that you obtain a head on both flips? Well, there's no and in that sentence, right? So we're thinking of a group of two coin flips, but we want to think of them as individuals. So you flip a coin, on the first one it's heads, and on the second one it's heads, right? The other way you can think about it, okay, tell yourself the story. So, okay, so this is what happened. I flipped a coin. It was crazy. I know, it's so crazy. I flipped a coin, and it went up in the air, and it came back down, and it was heads. And then I flipped a coin again in the air. It came back down. It was heads, right? So instead of thinking them as two heads, we think of it as one heads and a second heads, right? Hopefully you can start to see what we're talking about, the difference. This is not a group of two, it's individuals, a head and a head, right? So again, I'm just going to write maybe something for your notes. You do not need to write all this stuff on a test or anything, but this might be good to kind of think about them when it comes to, if you're looking back at your notes and have no idea what's going on, if you write these down, might be helpful. So instead of a probability of two heads, it's the probability of a heads and the probability of another heads. And when we have and, we're going to multiply. So that's what we meant by multiplying the probabilities. You take the probability of the first one, multiply it by the probability of the second one. And that's why we have to think of it as individuals. Because we think about it as a group, there's just one probability. That doesn't help us. But when we list them out as individual probabilities, right, then we can just multiply them. It's easier. All right. So what's the probability of getting a heads? Well, there's one heads on two sides of a coin, so 1/2. What's the probability that the second one is heads? Well, since they're independent, right? One coin flip doesn't affect another coin flip. Once again, that's going to be 1 out of 2. So when you multiply these together, you get 1/4, or you get 0.25. That's the final answer. So if that was a little confusing, let's think about it in a different way. So you won't be able to do the second way every time, but maybe it can help you kind of in your mind get it why it's 1/4 in this case. So let's talk about the sample space of getting 2 coin flips. So if you're doing 2 coin flips, what could you get? Well, both of them could be heads, right? Both of them could be tails. The first one could be heads and the second one could be tails. Or the first one could be tails and the second one could be heads. And those are the only ways, right? So what's the probability of getting both heads? Well, we see it's 1 out of a total of 4, which is 0.25. So same answer. And again, you won't be able to do this every time because what if I said 15 coin flips, right? That's going to be way too many. And that's why we have this way of doing it. All right, let's look at another one. In the game of roulette, the wheel has slots numbered 0, 00, and then 1 through 36. A metal ball rolls around a wheel until it falls into one of the numbered slots. So what's the probability that the ball will land on the number 17 3 times in a row? All right, so strategy, tell yourself the story. All right, actually walk through. Because you can't just say, if you really want to milk this story for all it's worth, right? Keep everybody on the edge of their seat. You don't just say, oh, I threw a ball and it landed at 3 times. No. Yeah, right? So, there I was at the roulette wheel. The ball went and it rolled around all the numbers. And guess what it got? The number 17. Crazy. And then it rolled again. And it rolled all the way around. And you will not guess what the next number was. Yeah, it was 17 again. And then the ball rolled around a third time. And you will not believe. I know. No, it's super crazy. It was another 17. What? Right? So this is what we mean, right? It was a 17 and a 17 and a 17. So a way to think about this, if we have the probability of 3 17s, that means the first time we got a 17, and the second time we got a 17, and the third time we got a 17. Right? So again, we're not looking at a group of threes. We're looking at an individual, right? A list of individual possibilities. We got a 17 one time, 17 2 times, 17 3 times. All right. So what's the probability of a 17? So it is not 17 out of 36, right? So first of all, out of all of these numbers, 0, 00, 1 through 36, how many times does 17 occur? Just one time, right? So 17 occurs one time out of how many numbers? Well, 1 through 36 is 36 numbers, 37, 38. So 1 out of 38 times. What's the probability the second one will be a 17? Well, this doesn't give us any indication that it would be a different probability, right? So these should be independent. So once again, it would be 1 out of 38. And again, 1 out of 38. So we multiply these three probabilities together, we get about, and that's what this little wavy thing means. You don't need to worry about that. I'm not going to take off on a test or anything, but it's going to be about. And what does our calculator say? So when we multiply these out, some of your calculators may say 1.82. But does that make any sense? Can a probability be more than 1? No, it cannot. So either you did something wrong, or you need to just keep looking. So on some of our calculators, if it says 1.8 on a probability question, you need to keep looking, and there should be an E at the end of that, right? And it would say E -5. Now, remember this E -5 means this is scientific notation, so you move it to the left 5 places. 1, 2, 3, 4, 5. So we get 0.0000182. And this is the probability. Let's do example 4. So a bag contains 4 blue M&Ms, 6 yellow M&Ms, and 3 green M&Ms. Find the probability of randomly picking and eating 2 green M&Ms. So again, tell yourself a story. Where's the and? I picked out from a bag of M&Ms, I picked out one M&M, and it was green. And then I picked out another one, and it was also green, right? So, probability of 2 greens. We have the probability that the first one is green, or times the probability the second one's green. All right. So what's the probability that the first one's green? Well, there's 3 green M&Ms out of a total of 13 M&Ms. Now, what about the next one? So notice we find the probability of randomly picking and eating. So this is without replacement. So some students, it's helpful to actually point this out, but you can actually write this, you can kind of think of it practically. So let's actually go through it. So we have 4 blue M&Ms. So 1, 2, 3, 4. We have 6 yellow M&Ms. So 1, 2, 3, 4, 5, 6. And we have 3 green M&Ms. So 1, 2, 3. All right, so these are all the M&Ms we have in our bag, and we take out one of them. And the one we take out is green. So there's 3 green ones out of a total of 13, and we take it out. So on the second time, since you ate it, now what's the probability of getting a green? Well, since we got what we wanted, we have 1 less green M&M, right? So that's going to be 2 green M&Ms out of how many? Well, since we have 1 less green M&M, we have 1 less M&M in general. So that would be 12. So 2 out of 12. When you multiply these together, you get 0.077, and that's our final answer. So if it's dependent, you might have to go down some numbers when it comes to finding your probability. If it's the same if it's the same thing 2 times, right? A green and a green, you might have to go down in both cases. All right, let's do problem number 1 on our word problems. So a tire factory that randomly selects a sample of items without replacement will accept an entire batch if every item in the sample is okay. In one day, a factory manufactured 2134 tires and 468 were good. If 5 tires are randomly selected for testing, what's the probability that the entire batch will be accepted? Okay, so what are you trying to find the probability of? That the entire batch will be accepted. Well, when will a tire batch be accepted? So some people just give up because it's a word problem. And I'm telling you, word problems in statistics are pretty easy because they tell you all the information you need to know. So we need to know when the entire batch will be accepted. And if you look at the question, right, the entire batch will accept, right? We will accept an entire batch if, so this tells us when it is. Every item in the sample is good or okay. So if we have 5 tires in our sample, then we need all 5 tires to be good. 5 good tires. All right, so how do we do that? Well, since it's more than one, tell a story. Right? So I looked at all the tires and I got one of them out and it was good. I got another tire, it was also good. I got another tire and it was good. Another tire was good. Another tire, good. Right? You got to think of them as individuals, not just a group. All right. So what's the probability of a good tire? So some people now will incorrectly say 1 out of 468. That is not correct. It is not 1 out of 468. Right? So let's go back and let's think about this. If you have what's the probability in this case of getting a green M&M? We didn't say it was 1 out of 3. We said it was 3 out of 13, right? It's the number of green divided by the total. That's what regular probability is. Don't forget. Very easy to forget once we start getting all these crazy numbers. All right. So if we're trying to find the probability of a good, it's going to be the number of good divided by the total. So that's the probability of one good tire. Times. All right. So we got to ask ourselves, is this with or without replacement? This is without replacement, right? Which means that we have to go down in tires, right? We took out a tire, so now we only have 2133, and that tire was good, so we have one less good tire. For the third one, we keep going down, right? We have one more less tire, and we have another, and we have another. And when you type all this into your calculator, you should see that we get about 0.0005. Okay, now notice, because some students think that the 5 needs to be in there somewhere, right? We need to have a 5. But notice, the 5 tires tells you how many probabilities you're going to multiply, right? Because we have 5 tires, we're multiplying numbers 5 different times. Just like up here, when we had 2 M&Ms, right, we multiplied 2 probabilities. So that's where the 5 and that's where the 2 comes into play. So it's not going to be 1 over 5 or 5 over something, right? It's just going to be 5 different probabilities. That's what the sample tells you, how many we need. All right. Does this outcome suggest that an entire batch consists of good tires? No, right? If the entire batch was good tires, then the probability should be 1, right? That means all of them are good out of the total. No, because only a probability of 1 would indicate that the entire batch consists of good tires. And it is nowhere near 1, right? Way smaller. Would it be unusual to accept the entire batch in this case? So we said if we are accepting an entire batch, it's when every sample is okay. And we saw that that probability is 0.0005. So would it be unusual to accept an entire batch? Absolutely, right? This is a very small probability. And specifically, right? Yes, because 0.0005 is less than 5%, right? 0.05. All right. That's done for this section. Make sure to watch the next video where we'll talk about at least one. Talk about some new ways of doing multiple trials. If you have any questions, like always, let me know. Have a great day.